Right, dude, we are live. What's up, guys? This is Dem Keys, and well, we are holy shit, dude. We are doing a fifth, I think. Yeah, I think a fifth. How do I even say this? We are doing how? Hold on. How do I phrase this? We have been on a roll. We have been doing talking streams for 5 days straight, and dude, that make voice crack. That makes me happy. That makes me super happy because I've been trying to get better at streaming, and well, fortunately, I have been able to stream. I've been able to do talking streams for the past 5 days. Well, 4 days. Cutane, hello, welcome to the stream. How's it going? I was just talking about how I'm happy that I've been able to do talking streams for the past 5 days, for like 5 days in a row. This is the fifth day, and soon even my mute streams will be converted to AI voice streams. So it's not going to be mute streams. There's going to be TTS. Why was that hard to say? There's going to be TTS speaking on my behalf. So in situations where I'm not able to do a talking stream, I'll do an AI voice stream instead. That being said, today we are gonna carry on learning about training, training a feed-forward neural network. Now, in yesterday's stream, towards the end, give me a second. Okay, in yesterday's stream, towards the end, I had these doubts. I cleared up this one, how an iterator is made. Apparently, the protocol to follow is that you make a class iterable by creating an iterator that the class's iter method can return, and then that iterator is responsible for, because the iterator also implements a next method, so that's why you're able to call methods like iter and next and so on to use to consume the iterator. And yeah, I cleared up my doubt about that. I also learned the exactly what keeps track of the count. In this case, it's the iterator. I also had a doubt in between that why do we need an iterable and an iterator separate? And it turns out that you can combine them. However, having them separate does have its benefits. One of them being that you can have multiple iterators. Um, you're not going to have one iterator bound to one instance of the object. So yeah, I'm happy I cleared up that doubt. The next doubt that I had was this: how exactly flatten works. Yesterday, I was having this confusion of what exactly flatten was doing, why it was flattening the data in the way that it was doing it. And it turned out that my confusion was because I misunderstood. So okay, let me show you. Let's how do I oh yeah. Um let's print out train. Actually, I think I need to run all of this again, and it's going to need to re-download that data set as well. So give it a second while it does its thing. Okay, that's done. Then we have to define this neural network. Actually, no, not this one. We have to define this one. This is our simple feed-forward neural network for classification. Then we load the training data. That's gonna start downloading the data sets. Okay, and I think it's done. Yeah, I think it's done. All right. Further from that point, I should be able to use this. So train underscore features dot shape. So my doubt was arising because of this shape, and it was my misunderstanding of what exactly dim zero is, or where exactly dim zero starts. Because for some reason, I was assuming that dim zero starts from like the innermost, like as in dim zero was the innermost dimension, and then going outwards we get dim 1 and 2 and 3. But it turns out dim 0 is the outermost dimension, and it kind of goes inwards, counting dim 1, 2, 3, and so on. So the way that flatten is working is by default start dim and flatten is it starts at dim 1. So that's why the result that we were getting was uh, let's flatten this. Oh wait, that starts at 0. Oh, okay. This is another interesting thing. If you call nn.flatten, this classes or methods, this classes constructor, it sets a default value for start dim, which is 1. In this case, it's set to 1. However, if you have a tensor and you call the flatten method on the tensor, start dim is set to 0 by default. So I feel like that can cause a bit of a confusion if you don't know that there's a default value. So okay, in this case, I'll set it to dim 1. And yeah, this is the result after you set it to after you flatten starting at dim 1. So it did exactly what it was supposed to do. In my case, the reason why I had a doubt initially was this. Hold on. Oh God, let's not do that. Yeah, initially my confusion happened because I was assuming that dim 0 starts here, but dim 0 actually starts here, the outermost dimension. And then dim 1 is here. So since we are specifying start dim 1, it starts flattening everything, including this. It flattens everything further from this point, all the way to whatever you specify end dim to be. And end dim is -1, which I'm assuming is another way of saying the end of the dimensions, like the very last dimension. So it goes from dim 1 all the way up to the end. So in this case, it flattens this entire thing into one contiguous array of values. So that was yeah, that issue that I was having, that confusion that I was having yesterday, was because of my, well, misunderstanding of where exactly dim 0 starts. And now that I cleared that up, I understand that as well. And the next thing I was doing was this. And I didn't finish looking into this because this kind of like took me, this made me do research on a bunch of other stuff, which I'm glad about, because every now and then I kind of have to give myself a bit of a refresher on various math related concepts that I haven't touched in a while. So, for example, logarithms. I I so unless I am able to remember, like I have to create my own definition of it to understand. The basic idea with logarithms is we are trying to find out to what power you have to raise a certain number to get a certain value. So, for example, how do I demonstrate this? So we are basically trying to find out the exponent to which a given value has to be raised in order to get a certain number. So, wait, I'm not able to create a cell. Okay, let's bring this down. Okay, so let's say, okay, we'll import from math import log. So we can do log. Hold on. So it's x, and then we have the base, right? The base is the thing that we are gonna give an exponent to, and we are trying to find the exponent. So in this case, let's say 16 and base 4. So what we are trying to find out here is to what number does the base need to be raised, or how do I say that? Yeah, like to what power? Because like we say 4 to the power 2, 4 to the power 3, stuff like that. So to what power does 4 need to be raised in order to get 16? And that value is basically the logarithm. So in this case, it's 2, because 4 multiplied by 4 raised to the power 2 basically means 4 multiplied by 4, and that's how you get 2. So finding the logarithm for how would we say this? Finding the logarithm for a base, because like in my mind, I've kind of like made that pattern where I'm going to be able to remember. I'm just trying to put it into words. So the logarithm is the value to which the base needs to be raised, or well, the logarithm is basically the exponent to which the base needs to be raised in order to get the input value. The input value in this case, let's say x. So I just need to remember this. It's basically the exponent. We are trying to find out the exponent that a base needs to be raised to in order to get a given input value. That's the logarithm of this value. Well, okay, how would we say this? That's the logarithm of this value given this base. Because like the base can be different, right? Oh, speaking of base values, another thing that I found out about is, and I haven't used this constant a whole lot. I learned about a new constant yesterday. It's the constant e. I don't know if that's, well, I think that's also called Euler's number. I was about to say epsilon, but I don't know if that's the same thing, so I'm not going to say that. But yeah, e is a mathematical constant for Euler's number, and when you are taking something called the natural logarithm, usually what you would do is log, let's say 16 e. So e is our base in this case, and then we're going to get that value. Actually, let's test this out. So what is e supposed to be? Yeah, this is our constant. It's 2.718. It's one of those things like how we have pi, the constant, which is 3.14, and then like there's like, I don't know, hundreds of digits after that, but the most common thing is 3.14, and then you can take how many ever digits you want after that. I don't know if pi should be a part of this, right? Yeah, that works. So there you go. There's some digits after pi. So just like pi, we have e, which I don't remember. Is it called a natural constant or something else? I know that it's called Euler's number, but let me just look it up so I can give you the right information. So it says here the number e is a mathematical constant approximately equal to 2.71828. That is the base of the natural logarithm and exponential function. Okay, so this is the base that you have to use if you're trying to calculate a natural logarithm for something. I'm still trying to figure out how I'm supposed to phrase that sentence. Like, oh, you know what? Okay. In terms of vocabulary, I can probably ask a language model. I think I have, yeah, I have this one open here. Let's refresh it. And select Sonar Pro. Okay. I've learned about logarithms. I learned that calculating a logarithm is, wait, I spelled that wrong. Logarithm. Calculating a logarithm is basically calculating the exponent to which a base has to be raised in order to get a given input value. So for example, log 16, 4 would be 2. My question is, or rather, but I'm having trouble with the vocabulary side of things. How exactly am I supposed to describe this in a sentence? Would I say the logarithm for 16 given a base 4 is 2? Or is there some other way to say this? Okay. Great question. You're absolutely on the right track with understanding the concept of logarithms. When it comes to describing logarithmic expressions in words, clarity and precision are important. Here's how you can phrase it correctly. The logarithm of 16 with base 4 is 2. This is the most common and mathematically accurate way to express it. Let's break it down. Logarithm of 16. So that basically means we are calling the log function and passing in 16 as an input. But you also have to give it a base unless it's using the natural, what do you call it? Natural exponent? No, what is it? Unless you're calculating the natural logarithm where you would then use e as a base instead of some custom base. Logarithm of 16 indicates the value you're referring to, 16, in relation to a logarithmic calculation. With base 4 tells you the base of the logarithmic function, and is 2 states the result. Okay. the exponent to which 4 must be raised to equal 16. Alternate phrasings. If you're looking for variations, here are a few other ways you could describe this. The base 4 logarithm of 16 is 2. Okay. In base 4, the logarithm of 16 equals 2. I'm probably not going to be using that. Okay, so it might seem silly to try and learn these different phrases, or try and learn different ways of phrasing this, but learning different ways of phrasing this also helps kind of create a pattern in my mind to where I'm going to be able to remember in the future exactly what a logarithm is. Because, dude, there are certain like basic concepts that I tend to forget sometimes because I don't use them nearly as often, or rather, I forget the names of certain concepts just because I don't necessarily call them that. Like, for example, when we say 4 to the power 2, 2 is an exponent that we are using, right? But I don't often use the word exponent. And so, let's say a couple of weeks down the road, or a couple of months down the road, when I come across the term exponent again, I'm like, okay, what was exponent again? And then I go back to Wikipedia, and then I'm reminded that, oh yeah, it's just the thing that you are raising a certain number to. So like when you say so and so to the power that, then it's, oh, actually that, okay, maybe I could try to come up with alternate phrasing for exponents as well. Okay, the exponent to which 4 must be raised to produce 16 is 2. I'm probably not going to be using that. Log base 4 of 16 is 2. I'm not going to be using that. I feel like I'm going to be using this much more. The base 4 logarithm of 16 is 2, because then we can also substitute this with whatever other base we are using. So for example, if we use e, then this becomes the natural logarithm of 16 is 2. Or, well, it's not going to be 2. It's going to be, hold on, let me go back to that thing. The natural logarithm of 16 is 2.7725, whatever. Okay. I like this. I like these words of encouragement. I hope this clears up any confusion. You're doing great. Appreciate the kind words. The language model doesn't give a shit, but like, it's nice to have a conversation with it. Okay, appreciate the kind words and the information. I was wondering, oh, I would like to also um, figure out the vocabulary around exponents, because I know that an exponent is the number to which a base is raised to get a value. So for example, oh, but I usually use to the power of type of vocabulary. I'm trying to figure out how to fit the term exponent into this. Into this. So for example, actually, no, this sentence should probably come later on. Okay. Wait, where's the cursor? Here. So for example, 4 raised to the power of 2 is 16. Okay, give it a second while it finishes its thing. Okay, done. You're absolutely right to want to refine your vocabulary. Understanding the terminology will help you communicate mathematical ideas clearly and confidently. Let's focus on exponents and how you might incorporate them, how you might incorporate the term exponent in your description. Standard power of vocabulary. As you've correctly stated, the typical way we often explain exponential expressions is with phrases like 4 raised to the power 2 equals 16 or 4 to the power 2 equals 16. Okay, yep. This description is perfectly fine and widely used. However, you can include the word exponent to make your description more precise and academic. How to use exponent in your... Okay, I'm not trying to make it academic. I'm just trying to, like, I mean, it's great that, you know, the model is telling me that, yeah, this can make it academic. But like in my case, I'm just trying to include it in there so that in my mind, I can form that pattern to where I associate exponents with to the power of. Because I don't use the term exponent nearly as often to remember that it's supposed to mean, you know, to the power of. And that's why every now and then I have to come back and look at the definition. Here's how you can incorporate the term exponent. Explicitly describe the exponent. The exponent is a number to which the base is raised to produce the value. For example, in the expression 4 to the power 2, I don't think they meant to write 42 here. I think that's an error in like the formatting thing. Like maybe he was trying to write 4 to the power 2 and then 42 also came out. But anyways, in the expression 4 to the power 2, the base is 4, the exponent is 2, and the value is 16. Or 4 raised to the exponent 2 equals 16. Combine exponent with the power of, or with power of. 4 raised to the power of 2 means the base 4 is raised to... So, okay, this is another thing, right? I feel like if I remember base, I'm going to remember exponent. So I need to like remember that, okay, in an exponential or in an exponential expression, I think, yeah, in an exponential expression, the base would be, well, in an exponential expression, the exponent would be the number that the base has to be raised to the power of. See, I wouldn't have this issue if the term exponent wasn't used in various other places, but the thing is I'm used to saying the power of, right? And that works perfectly fine, as the language model is saying as well. It's just that um, when you're looking at like official documentation for something, it tends to have more formal speak in it. And that's not necessarily a bad thing. It's just that, you know, if I'm not used to saying exponent, then I'm not going to remember exponent. If I'm used to saying the power of, I'm just going to remember, yeah, this is the power of. And well, then I don't exactly know what base is and what exponent is. So I need to be able to like incorporate that into my vocabulary. Or I don't even need to incorporate that into my vocabulary. I need to be able to like just somehow form that pattern. Like I already know what to the power of means, right? That's basic math. But I need to be able to like include words like base and exponent in there. Okay, rephrase to highlight the exponent's role. In 4 to the power 2 equals 16, the exponent 2 tells us how many... Okay, so it seems like It seems like when we try to add the term exponent into the mix, it's mainly just trying to describe the sentence. It's trying to explain the sentence. In this case, the sentence being 4 to the power 2 is equal to 16. It kind of seems like we're just trying to fit the word exponent in there. General vocabulary for exponents. Here are some common ways to talk about exponents mathematically. Base raised to the exponent. Okay, I like that. I like that. Base raised to the exponent. Nth power. Okay, that's also something that I've seen in a couple other places, but I don't use it nearly as often. Um, then power of, and then exponentiation, the general term for raising a base to an exponent. Okay, I didn't know that. Okay, all right. Suggested sentence. Here's how you might summarize your understanding, incorporating both power of and exponent. I think I missed the add timer. Hold on. Yeah, I missed the add timer. And okay, cool. There's an ad playing right now. So I'll take a hydration break and I'll see you guys in 30 seconds. All right, welcome back. Uh, where was I? I was saying something before. Okay, all right. Incorporating both power of and exponent. 4 raised to the power. Wait, was I reading? Okay. 4 raised to the power of 2 means that the base 4 is raised to the exponent 2, producing the value 16. Okay, all right, cool. Now, why was I talking about? Oh yeah, I was talking about how I learned about logarithms and relearn again and again, because logarithms are another topic that I don't use nearly as often to bother remembering. Like, I'm slowly getting better at remembering that, oh yeah, this is what it does. But like, the thing is, I don't, at least, in the past, I wasn't using it nearly as much. Now, I mean, with all the deep learning stuff, I'm definitely using a bunch of the other math concepts that I wasn't using before. I'm definitely using a bunch of them now. And of course, also learning new concepts. Um, yeah, logarithm. Dude, I forgot where I was going with that. So yeah, logarithm. Um, I got into learning. Oh yeah, so I refreshed my knowledge of logarithms because in cross entropy loss, which is a loss function in deep learning, logarithms are included. I think natural logarithm is what's included in there. I have the thing open on a different system, so I can't really show you guys, but I can like read it out. So I was learning about cross entropy loss. I was trying to understand exactly what is going on. So yesterday I had this doubt, right? I had the doubt. Let me scroll back up here. So the doubt that I had yesterday was this: we are able to pass in a batch of 64, not 64 values, but like 64 sets of values, right? Each set is basically an image that has been flattened. So we are able to pass in 64 such sets all at once to the neural network, and then the neural network processes them and gives out the output. And then we pass all of these outputs, this entire batch of outputs, which in this case the batch of outputs what it outputs is the classes. So if you look at the, and I hadn't noticed this yesterday, because in my mind I still kept thinking that it's returning one value, but I forgot that this is a classification. This is a neural network meant to classify images, and so what it returns is probabilities, meaning it's a set of values, and the value that has the highest score, that class is basically the winner. So we have a batch of 64 sets of values, and we pass that batch into the neural network, and then the neural network gives out a batch of 64 sets of values, but those sets of values are probabilities for each class. So there's 10 classes in total, which is why each batch contains 10 values, and then we look at the values in these sets, and there's also some more processing that has to be done before we can really use these values, but it gives us raw values, raw logits, before we pass them into the cross entropy loss function. Now, my question was, my doubt was, or my confusion was arising from the fact that we pass in a batch of 64 sets of values, yet at the end, the loss function just gives us this one value. So I was like, why exactly is that? And here is, you know what? Okay, I kind of want you guys to be able to read it as well. So I have the thing opened up in Gemini, just so that it remembers the conversation even if I close the browser. Because if I do it with Perplexity, it's not going to remember because I'm not logged in here. So here's what I'm going to do. I'm going to rewrite the question, and then we can read the answer here. Because so what this does, well, just so you guys know, a bit of a spoiler. At least on the Gemini side, what this did, and I'm explaining. I'm expecting Sonar to do the same thing, but what happened on the Gemini side is that I asked the question. Actually, okay, let me type out the thing. So I'm learning how to train a feed-forward neural network, or a fully connected neural network, with PyTorch, and came across cross entropy loss. I noticed in the example that the arguments provided to the loss function are of shape 64, 10, and, well, 64 as well, respectively. So in this case, 64 is that one single value. That's supposed to be the class. That's supposed to be the index of the class. What was I? Yeah, okay. Well, okay, not the, well, yeah, okay. It's supposed to be the index of, basically, the reason we are using numbers is because we are associating numbers with labels, and that's kind of how, like, that's what I mean by the index of the class. So a t-shirt will be 0, pants will be 1, a shirt would be 2. I'm just giving like examples that the actual thing might be different. Yeah, okay, respectively. But the function only returns one value. I'm very new to deep learning and don't even understand how this function works, so I'm kind of confused. Now, while this writes out its answer, spoilers, I found out that apparently cross entropy loss. The cross entropy loss function does a bunch of different things together. It's not like just one thing that's happening. It's a collection of different things that are happening together. And in the end, the value that's given is actually, I don't remember why the value is single. Well, the reason why the value is single is because after the calculations are done on like the 64 samples and then 64 values are produced, we basically take some kind of like average of those and then that gets passed out. So that's why we get one value, and then that, I believe that loss value is used by AutoGrad to calculate the gradient of the loss function with respect to whatever parameters, and then based on the gradient and using gradient descent, it calculates how much the weights and biases have to be changed. Right. So let's read this. So the nn.crossEntropyLoss function in PyTorch is essential for classification tasks, and understanding its behavior will help clarify why it outputs a single value. What? A single value despite the input and target tensors having shapes like so and so respectively. Okay, how cross entropy loss works. So we give it input tensors, which are logits. The input tensor has a shape NC, where N is the batch size, number of samples in a batch, and C is the number of classes. Okay, so is cross entropy loss like specifically for classification? Because it seems like it's kind of known here that N is the batch size and it's expecting a batch. It's not expecting one value. And then C is the number of classes. So it's expecting classes as well. So is cross entropy loss mainly for, oh, it says cross entropy loss is essential for classification tasks and understanding its behavior. Well, okay, all right. This tensor contains unnormalized logits, not probabilities. These logits will be transformed. Where was I? Okay. These logits will later be transformed into a probability distribution by applying the softmax function internally within the loss function. Okay. Target tensor labels. The target tensor has a shape of n, which contains the class indices ranging from 0 to C minus 1 for each sample in a batch. Okay, all right. These indices indicate the true class labels for each corresponding row in the input tensor. Single value loss. For each sample in the batch, the loss is computed using the formula loss equals negative log so and so. So I'm assuming that's a natural logarithm because there's no base provided. Softmax probability, true class index. Loss equals negative so and so so and so. All right. PyTorch computes this for all samples in the batch. Wait, so would I be able to like calculate this myself? I mean, I would be able to. Um, but like, would I be able to confirm this? I think I would have to make the batch size smaller. Okay, let's see what happens after that. For each sample, the loss is computed using the wait, that's the loss formula? It's a negative of uh, the natural logarithm of the softmax probability. Wait, back up. Softmax probability, true class index. Oh, yeah, wait, no, hold on. Hold on. So softmax probability is gonna return the same array that was passed into it, meaning we are then passing an array into the log method. So how is it one value then? Okay, let's see. PyTorch computes this for all samples in the batch and reduces the results to a single value using the chosen reduction method, which in this case is average. This reduction operation explains why the function outputs a single scalar, even though the input describes multiple samples. Okay, let's take a look at an example here. Suppose the input tensor has the shape so and so. Each row represents the logits for one sample across 10 classes. Okay, that's the probabilities, but those are raw probabilities. Those aren't. I'm not sure what the other thing is called. True probabilities. Oh, they call them they call them unnormalized because it's not between 0 and 1. So softmax basically returns the set of values that you give it. It's going to scale them down to where the sum of those values equals 1. So it's in that regard, it's normalizing those values. Okay, each row represents the logits for one sample across 10 classes. Okay, PyTorch applies the softmax function to convert the logits into probabilities and computes the loss for the class indicated in the target tensor. Okay, I feel like this is where I'm confused. How are we getting one value? So we pass this after passing this into after passing the raw logits, after passing the logits into the softmax function, we still get an array. It's not one value yet. Now, what happens after that? The softmax function, PyTorch applies the softmax function to convert logits into probabilities and computes the loss for the class indicated in the tensor. Okay. Nope. I'm still not getting it. No, so what I'm having trouble understanding is, let me go back to, so what I'm having trouble understanding is if we have this list, okay, and we pass this into softmax, so, I don't know, softmax equals nn.softmax. Wait, does this work? Yeah, okay. And then A equals, or I can say B equals softmax A. And then we can print out A and print out B. List object has no attribute dim. Oh, it needs to be a tensor? Okay. All right. User warning, implicit dimension choice for softmax has been deprecated. Change the call to include dim equals x as an argument. Well, okay, sure. So these are our, this is our softmax, the result of our softmax function. Now, my point is, we have logits, right? We pass that set of logits into, and this is for one sample, by the way. We have a set of logits for one sample, and then we pass this set of logits into the softmax function, and it returns the probabilities, but like it returns a set of the exact same size, but the values are probabilities now, right? So it's, the thing is, it's still a set of values. So which value is being used from here to compute the loss? Like that's kind of where I'm confused about this. If reduction equals so and so, then the averages of all the loss samples. Okay, why it reduces to one value? The purpose of the loss function is to provide a single value that summarizes the wrongness of the model's predictions relative to the targets. This single value can be used in backpropagation to compute gradients and update the model parameters. Okay, all right. Okay, I'm confused. What exactly happens after the softmax function has um, has calculated the probabilities? I guess I don't understand um, where it goes from there, because how exactly is that set of probabilities being used or being compared to how exactly is that set of probabilities being compared to um, what do you call the thing, compared to a single expected class index? Okay. After the softmax function calculates the probabilities for each class in a multi-class classification task, um, I just realized something. This is multiple classes. This is not, it's not one, it's not two, it's multiple classes, and that is why the neural network um, is able to do that so well. There's something to explore there. Hold on, no, because in terms of classifying things, like you could also use linear regression. I haven't used it for classification though. I need to look into that. Anyways, the process moves on to comparing these probabilities with the true class using the cross-entropy loss. Here's a breakdown of how this works. Softmax converts logits to probabilities. The output from the model logits is raw, unnormalized scores for each class. The softmax function transforms these logits into a probability distribution, ensuring that all probabilities are in the range 0 to 1. The sum of the probabilities for all classes equals 1. Okay. For example, if so-and-so, yeah, okay. All right, great. Cross-entropy loss compares probabilities to true class. The true class for each sample is given as an um, integer index. Example 0 for class 1 in Python indexing. Okay, all right. The cross-entropy loss focuses on the predicted probability for the true class. It calculates the negative log likelihood for for that probability. Focuses on the predicted probability for the true class. The formula for the loss of a single sample is so and so. For instance, if the true class index is 0 and the softmax probability for that class is 0 point so and so, the loss will be. So is it just taking the highest number, like whichever? No, like how does that? I don't know. Hold on, hold on. The loss will be so and so. Where does it get? Oh, the negative log likelihood is this. All right. batch-wide loss. In practice, this computation is done for all samples in the batch. If the batch size is n equals 64, the loss is calculated for each sample and then aggregated. Okay, we take the average. I got that part, but I'm still confused about this true class index thing. The loss function outputs a single value that summarizes how well the model's predictions match the true classes across the batch. I'm still not getting. I feel like I'm having trouble visualizing this. Let's keep reading, and then I can ask the question later. Why compare probabilities to a single index? The key here is that each sample belongs to exactly one true class. Okay. The softmax probabilities represent the model's confidence for each class, and we compare the confidence score at the true class index to evaluate how right the model is. The other class probabilities are ignored. The cross-entropy loss penalizes the model based on how well or poorly it predicts the true class. Why use logarithm? The logarithm emphasizes small differences in probabilities. If the model is confident but wrong, the loss will be very large. If the model predicts a low probability for the true class, the loss is also very large, or the loss is also large. This encourages the model to assign high probabilities to the correct class. By combining softmax and cross entropy in this way, the process is efficient and numerically stable. Okay, it says cross entropy loss. It kind of seems to me like the cross entropy loss here is basically just a negative of the natural logarithm, or what they're calling negative log likelihood, which I'm still confused about. Like, what exactly is going on there? Okay, so my doubt here, okay, I'm still confused. No, I'm still confused about, okay, let me just say I'm still confused. Let's take just one batch as an example. In this one batch, there are 10 values. These are the logits. This set of 10 values gets passed into the softmax function. Softmax function, which then returns this set as a probability distribution. My confusion is, or my doubt is, which of these values is being, which of the values out of the 10 in the set is being used, and how does it get compared to the true class index? Okay, um, right. That's a great question, and I understand the source of your confusion. Let's break this down step by step for one sample in a batch to show exactly how the probabilities from softmax are connected to the true class index. In your example, we have logits, 10 values. These are the raw scores outputted? No, the raw scores output by the model for a single sample. Let's say we have the following logits, okay? Each value corresponds to one of the 10 possible classes for this sample. Each value corresponds to one of the 10. Okay, all right. True class index. Let's say the true class index for this sample is 7. Uh, that is an integer indicating the correct class for the sample. Python uses zero-based indexing. Okay, all right. Softmax converts logits to probabilities. The softmax function is applied to the logits to compute the probabilities for each class. The formula for softmax for a single class is so. All right, that's fine. I don't need the formula for softmax. This produces a probability distribution over the 10 classes. For example, after applying softmax, we might get so and so. This means that the highest probability for this sample is for class 7. Is that true? Yeah, okay, so that would be 7, 8, 9. Yeah, so that's 10 samples. So this is the highest value. This means the highest probability for this sample is for class 7 with 0.75 something something. And the model is very confident that class 7 is correct. Okay, select probability of true class. The cross-entropy loss compares the predicted probability for the correct class to the true class. The predicted probability, which is 0.75, to the true class index. In this case, the correct class is 7. So the probability of interest is softmax 7. Oh, softmax is the result. Okay. Wait, the correct class is 7, so the probability of interest is so and so. Wait, the cross entropy loss compares the predicted probability for the correct class. Okay, so that's the predicted class to the true class index. In this case, the correct class is 7. Okay, so that's what has been predicted. So the probability of interest is softmax 7. Okay. Logarithmic transformation. The cross entropy loss penalizes the model based on how large or small. Wait, has it been revealed? Okay, so the true class index is also 7. Okay. The cross entropy loss penalizes the model based on how large or small the probability of the true class is. The probability for the true class is. The penalty is calculated using the negative logarithm. Oh, that's where, okay, now I get it. So it's just taking that one. So it's going to take the logarithm of 0.75. Okay, let's just confirm that it's taking the natural logarithm. I'm not sure if I got this right. So let's do um, what log, actually negative log um, 0.75 e. That is 0.287. Oh, yeah. Okay. So it's the natural logarithm. Well, it's a negative of the natural logarithm. Substituting the values. Oh, yeah. Okay. It's just, okay. All right. Got that. If the probability for the true class is close to, what is that supposed to mean? 1:1? I didn't get that. If the probability of the true class is close to, I think it means 1. The loss is small. The model is confident and correct. If the probability for the true class is small, the loss will be large. The model is not confident. Oh, okay, hold on. No, I'm still, hold up. Okay, so we calculate the loss. How, wait. So where in between all this is the true class index being factored in? So we are using, oh, we use the true class index as an index, or well, we use the true class index to index the result of the softmax function. That's what we are using the true class index for. Okay, all right. And then we are calculating the loss based on that. And if the probability for the true class is close to 1, I'm assuming this means 1, is close to 1, the loss is small. Okay. Example, the model is confident and correct. If the probability for the true class is small, the loss will be large. Okay, and then it goes into this batch-wide loss thing, which is just it's doing like a um, what do you call the average? It's just taking an average, so I don't need to read that bit. Okay, what am I trying to ask here? Actually, I need to take a tiny break. Um, I will be back in a couple of minutes. I'm just going to take a short break and I'll come back. Okay, I'm back. Now, we're getting close to understanding exactly like what is going on here. I'm like super close to it. Um it's kind of interesting. Like you are able to create a set of labels, right? And assign indices to them. And then, well, okay, um I guess the set itself doesn't matter. It's the actual like value that matters, because that value is not necessarily an index pointing to something. It is like the value. It is connected to a certain class, right? Um and yeah, you're able to create this set of values, this set of classes, and assign numbers to them and get or well, associate images with these numbers, and then get the neural network to learn that relationship. And it's kind of interesting seeing how sorry, it's kind of interesting seeing how the neural network learns this relationship. I don't know if I'm explaining it very well, because I'm like slowly starting to picture this in my mind. But anyways, okay. So I'm getting or well, I'm slowly starting to understand what's going on, but I still don't fully understand it. More specifically, I haven't understood what happens after negative log 0.75, which which is 0.287. How exactly or what exactly is this value, and how does this value get used? I understand the batch the batch wide process, so there's no need to go into that, but how I haven't understood what this value is. Well, I've understood what the value is. It's the loss, but like, how do we know like whether the loss is too much or too little? Because it seems like it's too little, right? 0.0.2 is a much lower loss. So like, is a score of close to zero good, or is a score of close to one good? I guess that's what I'm trying to find out. Great question. The value so and so that you computed in cross entropy loss for that particular sample. What the value so and so that you compute is the cross entropy loss for that particular sample. Okay. So that's the loss value. Let's break down what this represents and how it's used in the context of training a neural network. What does the value 0.287 represent? The value 0.287 is a measure of how well the model predicted the true class for the given data sample. Here's why. When the model assigns a high probability to the correct class, the value of so and so is low. I feel like okay. Um, I feel like the issue that we're having here, well, I mean, it's not a big issue, but like I've noticed this with like some of the past responses as well. When it when it has to format something in like a different format, like I don't know, maybe it's using latex to show the math expressions and stuff. I feel like when it has to do that, it kind of struggles a little bit in terms of formatting it and like incorporating that into the output, and then we end up getting like these double kind of things. Uh, when the model assigns a high probability to the correct class, okay, so its prediction was correct, its classification was correct. The value of so and so is low, indicating better performance. If the assigned probability is low, if the assigned probability is low, then the loss becomes much larger, penalizing the model for, maybe I should be saying penalizing. It's kind of weird because like you don't say penalty, you say penalty, right? But I don't often hear people saying penalize. I hear saying penalize. Whatever. Okay. Penalizing the model for being less confident or incorrect. Essentially, this value quantifies the distance or mismatch between the predicted probability distribution and the true class label. How is this value used? Okay, all right, now I get it. So that loss that we are getting, so I'm just gonna assume that the loss is supposed to be between 0 and 1, and then based on this loss, well, actually we don't do it. Autograd does it. During training, this single value, cross entropy loss for one sample, plays a crucial role in the learning process. Compute gradients, backpropagation. The loss value is used to compute the gradients of the loss function with respect to the model's parameters, weights and biases via backpropagation. Okay. These gradients indicate how much each weight in the network contributed to the error and thus how much they should be adjusted to improve predictions. Okay, that's interesting. I only knew, or well, I was assuming that the only thing that gradients do is tell us what direction to go in, but this is also mentioning that, well, I mean, okay, technically, yeah, technically that's still true. It's just that I didn't think about it in that way. Because, like, initially, the only thing that was running in my mind in terms of gradients was that gradients will tell you what direction to push the weights into, and probably also by how much. But I guess the by how much part is your learning rate. So like you set the learning rate. But yeah, the gradients generally tell you in what direction you're supposed to be pushing the weights. But I didn't think about it in this way, that the gradients indicate how much each weight in the network contributed to the error, and thus how much they should be adjusted to improve predictions. Okay, parameter updates. The optimizer, stochastic gradient descent, or ADAM, uses these gradients to adjust the model's parameters slightly, aiming to minimize the loss for the next iteration. The iterative process helps the model to improve its predictions over time as it learns to assign higher probabilities to the true classes. Intuition. Why logarithms? The logarithm in so and so. What? The logarithm in so and so emphasizes confidence. It penalizes low probabilities for the true class more strongly than medium ones. For example, if the predicted probability of the true class is 0.9, the loss is small. Hold on, what? No, wait, what? If the predicted probability for the true class is 0.9. Okay, yeah, okay. So the result is this. For a second there, I was confused. I was like, dude, 0.9 is so close to 1. How's that low? But then no, it's taking the negative log of 0.9, which is 0.105. So yeah, that's low. If the predicted probability is 0.1, the loss is much larger. Okay, right. So I did not know that it is not clamped between. Actually, I think at some point I was going to ask the language model that, hey, is the loss kind of like clamped between 0 and 1? But it turns out it's not. So it can be a higher value, and apparently this is a crazy high value. This property drives the model to confidently predict probabilities close to 1 for the class. What? I didn't, hold on. What? This property drives the model to confidently predict probabilities close to 1 for the correct class. Okay. Okay, I understand now. Thank you. I'm wondering if loss is usually clamped between 0 and 1, or does it go beyond those values as well? The answer is yes. We've seen, you know, an example of that. I don't know if it goes below 0. I'm not sure, but yeah, the answer is yes, at least for one of those. I just wanted to give a bunch of explanation, a bunch of extra information. Okay. All right. The cross entropy loss is not clamped between 0 and 1. It can actually exceed 1 depending on the scenario, especially when the model makes very poor predictions. Let's clarify why this is the case. Range of cross entropy loss. The lower bound is 0 when the model predicts a perfect probability distribution for the correct class, i.e. the predicted probability for the true class is 1. The predicted probability for the true class is 1. Hold on. Hold on. What does that mean? The predicted probability for the true class is 1. Oh, this is what it means. Um, so if the predicted true probability is 1, meaning, okay, hold up. So what I'm getting here is that um, if the model has at some point very confidently assigned a score of 1, a probability of 1 to like a specific class, what that means is that all of the others are going to be 0, because the probability distribution is between 0 and 1, right? It's distributed across that entire set. So if you give 1 to just one of them, then there's nothing remaining for the rest, so they're all going to be 0. This means that the model is extremely confident that it is, you know, it is that class, and it is so confident that it is assigned that value. Okay, then we take, so okay, this is interesting. Like the indices still come in, right? Because we are still using index positions to kind of, because like, okay, let me Where is it? So maybe I should do like a markdown thing. So we can do 0 is, I don't know, shirt. 1 is t-shirt. 2 is pants. 3 is jeans. 4 is, I don't know, let's say top. 5 is skirt. And then 6 is, I don't know, dress. Okay, so these represent, these are indices, right? These are indices, and we are trying to get the model to output for each sample. We are trying to get the model to output, in this case, 7 probabilities or 7 scores. And each score represents each of these indices. And these indices are basically um, how we connect how we connect the concept of shirt or t-shirt or jeans or dress to one of one of the cells in the score array, in the score list. These indices are how we connect these clothing items to those scores, right? So we are trying to get the logarithm, the negative log of okay, we are trying to get the negative log of um of the true class index of the softmax uh, array, right? The true class index of from within the probability distribution. And if that value, if the true class index, if the probability at the true class index happens to be 1, first of all, that means that the model has confidently assigned, you know, a perfect score to just one item. So the model is confident about it. But also, the score is going to be perfect because then the loss is 0. This represents a perfect model where no loss is incurred, no upper bound. Uh, if the model predicts very small probabilities for the true class, the cross entropy loss becomes very large due to the behavior of the logarithm. Shit, I missed the ad timer again. So there's going to be an ad playing, and well, now there's an ad playing now. So I'll take a hydration break, and I'll see you guys in 30 seconds. All right. Welcome back. Where was I? Okay, the cross entropy loss becomes very large due to the behavior of the logarithm. If the model predicts very small probabilities for the true class. Oh, so it predicts wrong. Okay. If it predicts wrong probabilities, first of all, are you even able to pass 0 into I don't know if you're able to pass 0, but okay, let's pass something small. Let's do 0.01. So that's the loss. The loss is massive. Can we just do 0? Nope, we can't. Okay. So what happens in a situation where the model is very, very confidently wrong? As silly as this may sound, what happens in a situation where the model is very confidently wrong? So it assigns probability 0, and it says that that's the true class index. No, it doesn't say that. It assigns a probability of 0 to the true class index, to the value at the true class index. And then we pass. Actually, yeah. It assigns a probability of 0 at the true class index, and then we pass that in. Man, this is a clever system. This is no, dude. This is actually a clever system. Hold on. This is a clever system because I'm slowly starting to understand how the loss thing is working here. Like you you know the index that is supposed to be you know the index that is the true index, right? And you are expecting the model to assign the highest score or the highest probability to the value at that index. And if the model has not done that, you need to teach it to do that. So you're essentially teaching it what these things are, what these indices are. I'm not sure if I explained that well, but like, holy shit, dude. That is, yo, that's crazy. This means that there's no theoretical upper bound for the loss as the penalty grows infinitely large for predictions that are highly confident but completely incorrect. Okay. Typical values. Cross entropy hold on. Words. Cross entropy loss often varies depending on the quality of predictions. Near 0 for good predictions, greater than 1 for poor predictions, especially in multi-class classification tasks where the model is both confident and wrong. Hold on. Where the model is both confident and wrong. I want to set up a model that is both confident and wrong. Just just for shits and giggles. Okay. Why cross entropy loss can exceed 1. Okay, yeah, I get that. I understand why it can exceed 1. Actually, okay, that let's still read on because I get why it would exceed. But let's still read on. For multi-class classification using softmax, the number of classes and the distribution of probabilities both influence the loss. If the model assigns a very low probability to the true class, example, softmax output for the true class is 0. Okay, so it assigned a very, very low probability to the true class. See, now suddenly true class and true class index and all, they're starting to click. They're all like my mind is now able to connect the dots. This is a large loss value, and it happens because the model is confidently wrong. Okay. Oh, you know what? Okay, so it's not that the model would be confidently wrong about what it assigned a high score to. It would be confidently wrong about what it assigned a low score to because we don't look at the high score. We look at the index. We look at the true index. We look at the value that is at the true index. So if it is confidently assigned the wrong value, or a low score to the true class index, because the true class, the value at the true class index, what we are getting here, what we are understanding here is that the value at the true class index is supposed to be as high as possible. And if it's not, that means the model is not doing a good job of classifying. And so you calculate the loss, and then based on the loss, you do the whole backpropagation thing and update your weights and then just run it back. Okay, in binary classification, the value of cross entropy loss is usually smaller due to only two possible outcomes, true or false. However, even here, the loss will rise significantly if the predicted probability is very far from the true label. Misconceptions about clamping. Some sources mention a range between 0 and 1. That's interesting. I didn't even know that some places do mention that. I was just making an assumption. But this is typically a misunderstanding or only applies to specific cases. In binary cross entropy, when the true label is 0 or 1, the model outputs probabilities near 0.5. The loss can stay small and under 1 most of the time. However, in multi-class classification with softmax activation, the loss scales with the number of classes and the probability distribution. The loss scales with the the loss scales with the number of classes and the probability distribution and is not clamped. That's an interesting that's an interesting way to look at it. The more classes you have, the bigger the loss can be, because the smaller the probabilities can be. Because that's what I'm getting. The smaller the value that you pass into log, the bigger the loss is going to be. I also need to look into why it's called negative log likelihood. Like, I need to see if there's something that I'm missing there or something that I don't know. Okay, cross entropy loss starts from 0, perfect predictions, but has no upper bounds. Has no upper bound. The value depends on how far the predicted probability for the true class is from 1. Wait, the value depends on how far the predicted probability for the true class is from 1. How far, wait, I need to, hold on. The value depends on how far the predicted probability for the true class. Okay, so because we have the true class index, we're going to be looking at the value at the true class index. And it says the value depends on how far that probability is from 1, because we are expecting it to be as close to 1 as possible so that it is assigning the highest probability to the correct class, to the true class. But the value depends on how far, okay, okay, depends on how far the predicted probability for the true class is from 1. For poorly performing models, it can easily exceed 1 or even grow very large if the model is confidently wrong. Understanding this helps realistic what understanding this helps set realistic expectations for loss values during training. Let me know if you need further clarification. No, it is clear now. Thank you. I'm wondering, what exactly is negative log likelihood, and why is it called that? Is it just the negative of the natural logarithm See, this is where that vocabulary thing, that the vocabulary thing that we were looking into in the beginning of the stream, this is where that comes in, because I could have said, like the model suggested, the base 4 logarithm, if the base was 4, but in this case the base is e, so natural logarithm. Is it just a negative of the natural logarithm of the input? Okay, give it a second, let it finish doing its thing. Actually, let me hydrate again because I've been talking quite a bit. Give me a second. Okay. Um, all right. So the negative log likelihood, dude, I should rename this stream to, um, I should rename this stream to studying cross entropy loss, because that's pretty much all we've done for this entire stream. Like we like dove deep into cross entropy loss, and we like understood every little bit of it, except that last part, which, I mean, I'm assuming it's literally just taking the average of all the losses. I can test that later on, because like that's what I've understood, that like it calculates all of the losses for like every single sample in the batch, and then it just takes the average of all of them, so it has one value, and then it can give that as the loss value. Okay, the negative log likelihood is a concept used in probability and machine learning to measure how well a probabilistic model predicts observed data. It is closely tied to the notion of likelihood in statistics and is widely used as a loss function in classification tasks. Let's break down what it is, why it's called that, and its purpose. What is negative log likelihood? Likelihood is likelihood. In statistical modeling, the likelihood measures how probable a set of observed data is, given a specific model and its parameters. So it's like a, well, no, okay, this is measuring probability. I was about to say, so it's like a loss function, which that's exactly what's happening. But no, it's more, it is doing the prediction, measures how probable a set of observed data is. Yeah, this seems to be doing the prediction. Okay, anyways, it is a product of probabilities. Okay. We are not gonna go into, actually I'm kinda interested in this. I kinda do wanna go into likelihood, because it seems like an interesting concept. Even like outside, just in like a general data science and stats, from like a general data science and stats point of view, the concept of likelihood seems kind of interesting. I'll look into this later. Actually, maybe I should make a note of this. Stuff for later. Um, study likelihood. Okay. Log likelihood. In practice, because likelihood is a product of probabilities, which are between 0 and 1, the result can become very small and prone to numerical underflow. Oh, it's because they're all small decimals, and so when you start multiplying them, they all kind of just like scale each other down. To simplify computation, the log likelihood. Wait, what? To simplify computation, the log of the likelihood is taken. The log of the likelihood. Okay, this converts the product into a sum, which is computationally more stable and convenient. Negative log likelihood. Most machine learning optimizers, example gradient descent, are designed to minimize loss functions. Since we generally want to maximize the log likelihood in a probabilistic model, the negative sign is introduced to turn it into a minimization. Okay, turn it into a minimization problem. In the context of classification with neural networks, the predicted probability for the true class is typically obtained from the softmax function. The predicted probability, okay, all right. The predicted probability for the true class is typically obtained from the softmax function, and the negative log likelihood for a single sample becomes this. Okay, I still need to read up on the concept of negative log likelihood itself, because it kind of seems like this. So this concept is meant for something else, but like it seems to fit in over here very well. Why is it called negative log likelihood? The name comes from the components likelihood, log, and negative. Likelihood describes the probability of observed data under the model. Log is the natural logarithm used to convert the product of probabilities into a sum to simplify calculations. It's used to convert the product of probabilities into a sum. That's interesting. Wait, is that what's happening here? I'm not sure if that's what's happening. Okay, negative. The minus sign is added to perform minimization rather than maximization, and the log likelihood for what? Minimization of the log likelihood for optimization purposes. Is it just the negative of the logarithm of input? Yes, mathematically, for a given predicted probability of the true class, so and so, this makes it the negative of the natural logarithm for the of the input probability for the true class. For example, so and so, so and so, so and so. Okay, the negative log likelihood. Okay, so that's. I think I was right when I was saying earlier that so this concept is meant for something else, but it seems to fit well for this. It seems to fit well within this specific. What do you call it? Within this specific use case. Um, I mean, it still has to do with probabilities, but like in a different way. Okay, the negative log likelihood function ensures that the loss is small when the predicted probability for the true class is high, closer to one. Okay, the large dude. I feel like understanding what true class and true class index meant here, that has really helped me understand like this thing, because you know what's interesting about this? It's like, okay, let's say fine, I deleted that thing. Give me a second. Okay. So this is like an arbitrary list. We could assign these indices like in whatever way we want. The order can be in whatever way we want, but what matters is the true index, right? We assign a true class index for any given image. And then we make sure that the neural network understands this. We make sure that the neural network understands that, hey, so and so data is associated with this label, and so other data is associated with this label. I don't know, dude. There's something I find really interesting about being able to do that. And it's kind of interesting seeing how we are able to make this neural network learn based on data that we have provided to it. Okay, let's carry on reading this. Uh, where was I? This property aligns with the goal of training. Hold on. Where the probability is so and so, so and so, and large when the probability is low, closer to zero. Okay, this property aligns with the goal of training, which is to maximize the predicted probability of the correct labels. This property aligns with the goal of training, which is to maximize the predicted probability. I need to read that again. I keep losing my train of thought as I'm reading it. Hold on. This property aligns with the goal of training, okay, which is to maximize the predicted probability of the correct labels. Okay, now I get it. Yeah. The idea is to make sure the idea is to get the model to predict correct, make correct predictions, predict correct labels. Why use negative log likelihood? Penalty for wrong predictions. Negative log likelihood heavily penalizes incorrect predictions with low probabilities for the true class. For instance, yeah, okay, we saw that. Probabilistic. Yo, encoders, hello, hello. Thank you for the raid. Welcome in, encoders and community. Encoders and raiders. Yes, yes. Hey, how's it going? Thank you so much for the raid. Thanks for bringing your community here. Hello, everyone. I'm Dem Keys. I do co-working and study streams, and these days I'm mostly just studying data science and deep learning, and I'm actually studying that right now. Today we are doing. Today we were diving into cross entropy loss. I was trying to understand what exactly happens during cross entropy loss. So we kind of like took it apart and looked at the various different operations that happen and tried to understand exactly why things are being done the way that they're being done. Give me a second. Let me do the shout out thing. So if anyone is not already following encoders, go check them out. If you like their content, drop a follow. And yeah, hang out in their streams. Encoders, thanks a lot for bringing your community here. Did I ask what you guys were doing? Yeah, let me know. Let me know what you guys were up to today. And yeah, if you need to, I don't think I've ever said this before because I don't usually get rated. So like, there's a couple of things that like I need to remember to say. If you need to do after stream care, if you need to step away for some time and go freshen up and whatever, if you need to raid and run, it's all good. You do what you've got to do. Even raiders, if you need to bounce, it's all good. But yeah, enjoy your stay. So negative log likelihood. Where was I? Probabilistic interpretation. Negative log likelihood has a clear interpretation in terms of probabilities and likelihood, making it suitable for tasks where uncertainty and probabilistic modeling are involved. Hold on. Has a clear interpretation in terms of probabilities and likelihood, making it suitable for tasks where uncertainty and probabilistic. Encoders, hello, hello, welcome. Thank you for the raid. How are you doing? Let me know what you guys were up to today. What were you doing? What were you guys discussing? we are we've spent pretty much the entire stream studying about cross entropy loss because I was interested in understanding what was going on behind the scenes and why we were getting whatever values we were getting. Um, it okay. So the funny thing is, this whole thing started out with my doubt. Wait, encoders, you said we were talking about great expectation, a data quality tool. That's interesting. Let me, you know what? I'll look that up. I'll look that up later on. A data quality tool. Actually, I could write the, because I have to look into likelihood later on. Great expectation. Yes, we have been diving into cross entropy loss, and yo, I'm so thankful for language models because pretty much the entire time I've just been asking questions to Sonar, which is this thing here. By the way, if anyone wants these models are being hosted by Perplexity. So if you guys just want random access to a language model without needing any account or anything like that, just go to labs.perplexity.ai. I don't know if the yeah, they're very useful. Yo, it is insane how how many of my doubts I've been able to clear, at least in terms of, data science and coding and stuff like that. Stuff that I know the model is gonna give me good and proper, accurate answers about. It's been super helpful because like I had so many doubts about cross entropy and why things were being done the way that they were being done. Um, it answered so many questions. The funny thing is, in the beginning of the stream, my doubt was it wasn't about how cross entropy works. It was about why cross entropy gives us a single value, even though we are giving it multiple values. Like usually, what we do is we, at least in this example, um, in this example, we had like a batch of 64 samples, and for each of those samples, we have like a list of probabilities, right? Um, and then we pass that entire list of probabilities into the cross entropy loss function, and it then outputs one value. So I was confused about exactly what is happening there, and so I started diving deeper into it, and yo, this entire stream has been productive as hell. It has been it has been super productive. Okay, uh, you said a couple of days ago I watched a video about the intuition behind cross entropy and KL divergence. It's it was very well explained. I can link it to you if you want. Is the thing on YouTube? I can look it up. Give me a second. Actually, I can write this down as well. I'm interested in KL divergence as well. I don't think I've looked into that. Divergence. Thank you for mentioning the name, so I know that I'm looking at the correct video. Artem something. Oh, I should have mentioned. Yeah, there's no links, so like Nightbot is gonna delete the thing. But yes, thank you for that. I will watch this video after the stream. Yes, yes. Thank you. Yeah, it's fine. It's fine. Don't worry about that. I'm thanks for the recommendation on the video. I'm definitely going to check this out, and I'll also look into what KL divergence is. Oh God, hold on. It's playing. Okay. Oh, what was I what was I saying? Yeah, okay, hold up. So we are just about done learning about cross cross entropy, and I have a bunch of like exploration and a bunch of experimentation to do. Let me also add this person's video to the list. The key equation behind probability. Oh, that sounds interesting. The the key equation behind probability. I'm gonna check this out. Yeah, yeah, I'm gonna check this out. There's a ton of I'm super happy with the progress that I've been making with neural networks. I recently just got back into it after taking a hell of a detour through various other things. Now I've gotten back into it. Give me a second. Just a minute. Okay, yeah. So now that I understand um, now that I understand cross entropy, what's the next thing we were supposed to do? Yeah, okay, so in the where's this thing? So in here we calculate the loss, right? There's the test loop, there's the train loop. Okay, in the train loop we calculate the loss. Uh After getting the loss we call backward, and then okay, backward is supposed to compute the gradients, I'm assuming. And then optimizer is what's supposed to actually use gradient descent to change the weights and the biases. And then we reset the gradients. And if batch so and so, then wait, what does this do? So batch is the index. If this is 0, loss current loss item, so and so, so and so. I think this is meant to output some kind of score. Yeah, loss, and I'm assuming that's decimal places. Okay, current size. What is size supposed to be? Size is supposed to be the batch size, right? Size is supposed to be the size of the entire data set, not the batch size. Yeah, I don't think it's the batch size. I think it's the entire data set. Current. What is current supposed to be? Batch multiplied by batch size plus this. So batch is the index um, multiplied by the batch size, okay, plus so and so. Okay, I'm gonna need to like see this actually in action in order to understand what's going on. Also, what is loss dot item? Let's look into. So loss is the loss function, and the loss function returns. Give it a second. So when we call this, what type of object is returned? Loss. Okay. log softmax. Okay, note that this case is equivalent to applying log softmax on an input, followed by this. Wait, that's what's going on here, right? So okay, something occurred to me. I didn't look at the PyTorch implementation of it. Like I haven't read this documentation section. So far we just spoke to the language model and it explained everything, but like we haven't looked into whether it's implemented in that exact same way here or not. There is this last step as well that I need to remember, which is the reduction, where it just takes the average. Or well, I mean, okay, we could it could be either one of these apparently, but the default I think is mean. Wait, sum is supposed to be like literally sum, right? Or does sum mean something else? Reduction. Okay, mean is the weighted mean of the output. Sum is the output will be summed. Okay, all right. Okay, so I need to read up on this further, and then what more do I have? So okay, I had the doubt about item. Now, what what gets returned? You know what? I could just check that myself. Right? Is it some kind of um? It's a tensor. Oh, dot item is a way to access the value. It's this. Yeah, it's the way to access the value. I forgot that tensors have that thing where like if you want to access a specific value, I think you can also access the entire tensor list in this way. I don't remember. Hold on. Let's do a equals tensor 1 2 3 4, and then a dot item. What gets returned? A tensor with 4 elements cannot be converted to a scalar. Okay. What if I say that? Okay, there's something I'm missing about item. Does item only work for one value? I think that was another thing, right? Because um, a tensor can be converted to a list, if I remember right. I don't remember what the method is called. Okay, that's the method. So a tensor that contains multiple values can be converted to a list. But if it's one value, then you need to use item. Um, hold on. Actually, would this work? Yeah, this works. Okay. Let's just take a look at tensors documentation real quick. Where can I find tensor here? Okay. Tensor. Oh, I don't know what that was. Hold on. Hold on. Give me a second. Oh, it's just some kind of Google error. I'm not sure what this is. Um, I'm not sure why it's giving that error, but yeah, I'm just trying to look for tensor. Okay, search is search is being a bit of a pain. Tensors, there it is. And then under tensors, so I need to tensor. Okay, torch.tensor.so-and-so. Okay, okay. Man, hold on. PyTorch tensor item. Much better. Okay, this returns the value of this tensor as a standard Python number. This only works for tensors with one element. There you go. Doubt cleared. Awesome. So now I need to wait, where's the okay. So that is the loss, and then that's the batch index. For some reason it's being multiplied by the batch size, and then we are adding the length of this. I'm gonna have to look into this. Actually, I could do it right now, right? The batch size is, hold up, where's the batch size being calculated? I know that the batch size is 64, but just to be sure, where's the, oh, never mind. This is the output. Okay. So, okay, okay, okay. Oh, this is what it was saying. Okay, now I'm getting it. And this is the loss as well. So it seems like it's gradually reducing the loss, but that's kind of interesting. The loss still seems to be at like 2. Oh, is it because of it only being 10 epochs? That might be it. That might be it. Oh, back up. No, no, no. Hold up. I'm mistaken. Hold on. It's 10 epochs, but then how many batches? So it says there's how many of these? There's what? 4, 8, 10. So it's 10 epochs, but in each one it runs a training and then a test as well. What's happening in the test? Okay, okay. I'm gonna need to look into this more. Um, hold on just a minute. Okay, you know what we're gonna do? We have rated this person before. It's a person named It's Hewi. Um, their streams are super super chill. Um, so we are gonna go raid this person. I'm gonna be ending the stream here. Dude, it is it's been a good stream. It's been a productive stream. Do stick around for the raid. I would appreciate it. But if you're not able to, that's perfectly fine. And coders, once again, thank you so much for the raid. Thank you for bringing your community here. And yeah, I appreciate you raiding in and hanging out and chatting. Cutane, thanks for stopping by. Anyone else who might have been lurking in the chat, thanks for hanging out. It's been a productive stream. It has been a productive stream, and I'm so happy about that. Hopefully, I'm able to stream again tomorrow as well, and hopefully, it's going to be a talking stream. I don't know yet. Let's see. I'm hoping for the best. Um, yeah, yeah. That's going to be it for today. I hope you guys have a nice day, and I'll see you all next time. Peace.